Hello guys, my name is Teksim and today I'm going to cover the topic of 9.3, the applications of differential equation. So the table of content for my presentation will be divided into 5 parts. So first it's going to be the introduction, the 4 applications of the first order differential equation, followed by the motion with resistance proportional to the velocity. Third is the inaccuracy of the exponential growth population growth model. Fourth is the orthogonal trajectory, and last but not least, the fifth one is going to be the mixture problem. So let us move on to the first part, which is the introduction. So the applications of the first order differential equations are divided into 4 parts. The motion with resistance proportional to the velocity, the inaccuracy of the exponential population growth model, the orthogonal trajectory, and the mixture problem. So as we have learned from the previous topic of the differential equation, we know that differential equations is one of the most fundamental things to learn in mathematics. It can be used in many different areas of studies such as engineering, business, chemistry, and so on. So with that in mind, there are 4 applications of the first order differential equation. So specifically talking, we are focusing on the first order differential equation. So things will be different if we were to talk about the second order or the nth order differential equation. So aside from that, let us move on to the second part, which is the motion with resistance proportional to velocity. So concept number 1 is that we can safely assume that the fact that the resistance made by a moving object is proportional to the object's velocity. And concept 2 is it's related to the Newton's second law of motion, where F is equal to ma, and it can be written as F is equal to m times the derivative of v with respect to t. So continuing with the concept, if the resisting force is proportional to the velocity, we have F is equal to m times dv over dt, or equal to the negative of k times v, or dv over dt is equal to the negative of k divided by m times v, where k is always greater than 0. So this is also has something to do with the exponential change differential equation. So we'll use v equal to v0 and t as at times t is equal to 0 to solve this equation. So we have the equation of v is equal to v0 e to the power of the negative of k divided by m times t. So the velocity can also be represented as v. V is equal to ds over dt, which is the derivative of the distance equation with regard to the time. So then we'll have ds over dt is equal to v0 e to the power of the negative km times t, and times both sides by dt. It's going to be ds v0 e to the power of the negative km k divided by m times t dt. So after that, we're going to apply the integral on both sides, which is going to be the integral of 1 ds, and it's equal to the integral of v0 e to the power of that dt, and we'll find the s equation for that. The next part is that we assume that we let s is equal to 0 and t is equal to 0. So the whole equation would become 0. It's equal to the negative of v0m divided by k times c, divided by k plus c. So in this case, we can find c. In this case, it's equal to v0 times m divided by k. So if we substitute c in the s equation, we'll find the whole equation for s, which in this case, as shown in below. So in order to find how far the distance the object will travel, we take the limit of st, where t tends to infinity. So as t tends to infinity, we find the limit of s to t, and we can find the distance costed formula as v0 times m divided by k. So moving on to our example. For our example, we have for a 192-pound ice skater. The K in equation 1 is about 1.3 slug per second, and M is equal to 192 divided by 3 is equal to 6 slugs. So they ask how long it would take the skater to coast from 1 feet per second to from 11 feet per second to 1 feet per second, and how far will the skater coast before coming to a complete stop. So we'll use the equation we have, and the given things are K, M, V0, and V. So hence we plug in the formula, we get 11 times e to the power of 1t divided by 6 times 3 is equal to 1, which in this case is equal to e to the power of t divided by 18, negative t divided by 18 is equal to 111. And by applying natural log on both sides, and by after that we find t to be about 43 seconds. So the distance coasted would be 198 feet. So moving on to the third part, which is the inaccuracy of the exponential population growth model. So the formula for the law of exponential change is dp over dt is equal to kp, where p0 is the same as p0. P represents the population at time t, and k represents the continuous growth rate. And k is always greater than 0. P denotes as the population size at time t is equal to 0. So the formula of P in this case would be as shown in below. P is equal to P0 times e to the power of kt. So then dp over dt is equal to kp. From this equation we can divide both sides by p. Then we'll have the new equation for k, the relative growth rate. So if we look at one example of it, so this table gives the world population mid-year from the year 1980s to 1989. So taking dt is equal to 1, and dp, the approximately of the delta p, we can see from the table that the relative growth rate, from the equation dp over dt divided by p is equal to k is the approximately the constant of 0.017. So thus, based on the table data with t is equal to 0 representing the year 1980, t is equal to 1 representing 1981. So in this case we get dp over dt is equal to 0.0017, and p0 is equal to 4454, and p is, so then we can write p as 4454 e to the power of 0.017 t. So then we can predict that in 2008, where t is equal to 28, we can plug that 8 in, then we'll find the population to be approximately around somewhere around 7,169 million. So moving on to the fourth part of my presentation is the orthogonal trajectory. So the orthogonal trajectory is defined as a family of curves, which a curve intersects each curve of the family at right triangle or orthogonally. So the orthogonal system, curve system, is particularly important in physical problem involving electrical potential, where the curves in one family correspond to the strength of an electric field, and those in order to correspond to the constant electric potential. So let's look at some example for it. So the example asks to find the orthogonal trajectory to the family of curves y is equal to kx. So first we'll start by using implicit differentiation to take the derivative of both sides. So in this case we'll get dy over dx is equal to k, and then from the original equation k is equal to y over x, hence dy over dx is equal to y over x. So the slope of the original family is equal to dy over dx is equal to yx. So if we want to find the orthogonal trajectory, we know that they are perpendicular to our family everywhere. Then we want a slope for the orthogonal trajectory that is perpendicular to the slope of the original family. So in this case, we'll take the negative reciprocal of it. So the slope of the original orthogonal trajectory, dy over dx, is equal to the negative x divided by y. Hence, dy is equal to the negative of y of x divided by y dx. After applying integral on both sides, and then we'll find the solution to it, which is x squared plus y squared is equal to c. So moving on to the fifth problem of my presentation, which is the mixture problem. So assume in a liquid solution runs into a container containing a liquid or gas solution and possibly a specified amount of the chemical dissolved. Stirring keeps the mixture uniform and it flows out of the container at a known rate. It is frequently necessary in the process to know the chemical concentration in the container at a given time. The formula serves as a foundation for the differential equation that describe the process. So in this case, we have the formula below. And so if y of t is the amount of chemical in the container at time t, and Vt is the total volume of the liquid in the container at time t, then the departure rate of the chemical at time t is, we can find it as the formula below. And then going back to our original formula, we can find that dy over dt, it's equal to the chemical's arrival rate minus the y of t divided by v of t times the outflow rate. So let's look at some example of it. So the example asks, in an oil refinery, a storage tank contains 2,000 gallon of gasoline that initially has 100 pound of the additive dissolved in it. In preparation for winter weather, gasoline containing 2 pounds of additive per gallon is pumped into the tank at a rate of 40 gallon per minute. The well-mixed solution is pumped out of it at a rate of 45 gallon per minute. How much the additive is in the tank 20 minutes after the pumping process begins? So let's look at the solution of it. So we'll let y be the amount of the additive in the tank at the given time t. So we are given y of t is equal to 100 at t is equal to 0. The number of gallon of gasoline is can be written as Vt is equal to 2,000 plus 40 minus 45 times t, which is 2,000 minus 5 of t, 5t. So the formula would be the rate out is equal to y of t divided by v of t times the overflow rate. In this case, it's y divided by 2,000 minus 5t times 45, and the rate out would be 2 times 40, which is it's equal to 80 pound per minute. So the differential equation for this process is dy over dx is equal to rate out minus the rate in, which is 80 minus 45y divided by 2000 minus 5t. So we solve for the differential equation dx or dy over dx, and we label it as the equation 1, and we get pt is equal to 45 over 2000 minus 45t, and qt is equal to 80. And then we'll find v using the we can find the integral. We can use integral to solve for it. So then we'll get the final equation to be y is equal to 2 times 2000 minus 5t plus c times 2000 minus 5t to the power of 9. Then plugging everything in and then plugging 20 in the final equation, after we find C, then we'll find the y of t to be somewhere around 1,342 pounds. So thank you for listening to my presentation. If you have any question, you can feel free to ask me via my email or my social media account. Thank you.